contest medium difficulty solutions. So this is last weekend contest problem about count nodes equal to average of subtree. Let's read the problem. Basically, we got a root of binary tree. And then we are asked to return the number of nodes where the value of the node is equal to the average of the values in subtree. And this is the details of the definitions of these definitions. What is average? Average is n elements is the sum of the n elements divided by n rounded down to the nearest integer. So it is a math floor. A subtree, what is a subtree? A subtree of a root is a tree consisting of the root and all of its descendants. So it means a subtree of a node including itself and all of the descendants, all of the nodes below it. For example, let's prove our understanding by running through the example. So 48016. So this is the explanation. There are 5 out of this that has the nodes which has the same average values with the descendant. So to make it easy, let's start from the bottom because the bottom has less descendants, right? So 0, okay, it starts with 6. 6 is by itself, so 6 divided by one node. So subtree is including itself, remember? That's why it's 6. The same with 1, the same with 0. So that's why 6, 1, 0 fulfilled the conditions of the average actually the same with the average of the subtree is the same with the node value itself. So thus we got 3. Now the 5 subtree are 5 and 6. 5 and 6. And when it is divided by 2, 2 is the total numbers of the nodes of the subtree. It is rounded down and we got 5. So 5 is equal to 5. That's why it is included into calculation. So now we got 4. How about 8? 8 subtree are 0, 1, and 8. So a total sum will be 9. And 9 is actually, when we divide it by 3, it will be 3. And 3 is not the same with 8. That's why 8 is not part of it. How about 4? 4 subtree is the whole tree itself. And hence, we actually need to sum everything here. And then the total nodes there are 6 nodes. When we do this, we got 4. And 4 is the same with 4. That's why 4 is included into the solution and totally we got 5. So that's the problem. Now let's think about the tactics. So one of the challenge here is that we got to get all the descendants, right? Because if it is just a direct children, it's quite easy. Basically, when we try to solve the tree, think about how to traverse the tree. For example, in this case, it means that we need to actually traverse everywhere, and then whenever we traverse everywhere, we can build it from bottom to the top. It means that the easiest is to calculate first the leaves, right? After we calculate the leaves, the resulting, we can bubble it up. Now we got the roots. So basically we need to consider the the relationship that we can build out of it. So if you notice that 4, we can calculate 0 directly, so it's like the terminal conditions because it is by itself. There is no more children. There is nothing more to consider. So we can just divide it by itself. That's part of the solution. 1 is also part of the solutions. 6 is also part of the solution, which we can directly calculate it. But how about 5? To calculate 5, we need to know the 6. What was the 6? The 6 is itself, so it's pretty straightforward actually to calculate 5. So whatever result from the 6, we can use it to calculate the 5. It means that now the total sum will be 5 plus the total sum from 6 divided by 1, which is 5 itself, plus the uh, the total size of the nodes from 6, because 6 is by itself, it's just 1. So that's the recursive condition. How about 8? 8 means we can calculate 8 after we calculate 0 and 1. Basically, we need two things to get average, the sum and the size of the node. The sum means we just need the sum from 0 and the sum from 1, and we sum it again with the node value itself. How about the n, or the size of the subtree? The size of subtree for 8 means 1, which is 8 itself, plus the size of the node coming from 0 and the size coming from 1. It will be 1 plus 1 plus 1, 3. And then after we got the sum and we got the size, we can calculate the average and do the check. How about 4? 4, once we already calculate 8 and 5, and we store the value of the sum and the n, 4 is the same. Once we already get this calculation, in order to calculate 4, it will be first calculating the sum. In order to calculate the sum, it will be 4 plus 8 plus whatever plus the total sum from this 8 and plus the total sum of the 5. 5 total sum will be 5 plus 6. Total sum of 8 will be 8 plus 1 plus 0. And that was calculated before. So after that, the total size of the node, it will be 1, which is the 4 itself, plus the total node from subtree 8, and plus the total node of subtree 5. Once we got the total sum, the total node, we can do the average. So basically, that's the logic of how to do it, the relationship, which basically saying the value of the node is the sum of the sum value for that node is the sum of the value itself with the children, and so forth. Now let's go for it. So this is coder path. Basically, I'm trying to give explanation through the toolings here. So just now is 4851. Basically, I just need a writing actually. So what it means just now, if I'm putting it in writing, the total sum of the node is actually have the relationship of the node value itself plus the total sum of left children plus the total sum of right children. And then the total n, or the size of the node that you are looking at, is having this relationship, similar relationship. Okay, and once you got that, you just need to do the check. What is the check? The check will be whether the value of your node is equal to the math floor, which in Python you can do by this double slash forward. If it is, then it's part of the solution. So that's basically the gist of the relationship, which is the main idea on how to solve this. Once we got that, let's write the code, which I already prepared before. Essentially, we can do a recursion here. A depth first search will be used uh, to 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 describe to do the traversals downward, and for each traversals we basically describe the relationship. So this is the initialization for each node, that the total, sum, total, and total counter, because this is basically the one that we are looking for, which is the total one that has the average equal to the node value itself. So everything started, of course, with the node value itself, total size of 1, and the counter is 0 because we haven't do the check yet whether this node is part of the solution. And then what happened is, for each children that exists, we do this because it could be that the children doesn't exist, which is represented with null, right? In Python it will be none. And then for each of them, we do a recursion where we do the same thing for the node child itself. And then the node child later on will return us its value of sum and counter. And what happened is we accommodate those child values into our totals. After we accommodate our totals, we do the check for the node itself. If the node fulfilling the conditions, then we increase further the total counter by 1. So the total counter has been added from the node child, then further we plus it 1 if it fulfills the conditions. After that, we just return everything back. And what happened here? We just need to execute the DFS functions and grab the total counter and return it back. Then let's submit. So it is accepted. So basically that's how we solve it, and this is the full writings about how to solve it based on the tactic we explained before. And how about the big O time analysis? Big O time analysis, basically we just need to first analyze component per component, and then we aggregate everything. Okay. So let's analyze from the DFS node itself. So the subfunctions. If we notice, this will go for the node child. And for each node child, everything here is just a big O1 except for the recursion here. Right? The recursion here will at most visit the children one at a time. It won't go duplicated children. So actually, when you think about it like that, the DFS here will visit everything, every part of node by 1. So that's why it's a big O n, where n is the size of the tree, the whole tree. And we don't revisit the same n again and again. That's why it's big O n, where n is the size of the tree. Now, is there anything else here? Nothing. So that's it. It's big O n, where n is the total number of nodes in the tree. That's for the time complexity, and that's it for this problem. Hope that's helpful. Bye.